Welcome to Precalculus Concept 16G. We're going to identify slant asymptotes. So far, we've talked about vertical asymptotes, we've talked about horizontal asymptotes, and now we're going to talk about the third and final kind of asymptote in this class, which is going to be a slant asymptote. We've got three boxes, so here we go. First of all, let's just take a look at a picture of a slant asymptote. So I have the rational function graphed for you, f of x equals x squared plus 1 over an x plus 2. That's the red part of the graph that you see. And then I've labeled here for you the line y equals x minus 2, which is the slant asymptote. Now again, it's the same idea, right? It's that as your x values get bigger and bigger, your function, which is the red part, behaves more and more like the asymptote itself. The only difference is that in this case, it's on a slant, and I'm going to talk about how to find them and what they're looking for. It is to note that all equations of slant asymptotes are just lines. Y equals mx plus b, and you know what? We are really good at solving lines. So that's where we're going, you guys. Okay, so I have two examples for you here to demonstrate how to even identify and find a slant asymptote. You may recall that before we talked about the degree of p of x divided by q of x. And in this case, the degree of p of x is 2 and the degree of q of x is 1. It is very important to have a slant asymptote that the degree of p of x be exactly 1 degree higher than the degree of q of x. All right, exactly 1 degree. If it's more than 1 degree difference, then we can't find a slant asymptote. So it must be true that the degrees are separated by a value of 1 and that p of x is higher than q of x. If that's the case, then a slant asymptote exists and we can proceed. The way that you find a slant asymptote, you guys, is by long division. I know you're like so happy right now to hear that. So we're going to do x squared plus 0x plus a 1. Notice I have my 0x in there to be a placeholder, and we proceed as we already know how to do. Okay, x goes into x squared x times x is x squared. X times negative 1 is negative x. We draw a line, and we subtract. X squared minus x squared is 0 by design. 0x minus a negative x is 0 plus x, so this is going to be plus x, and we're going to then bring down the 1, positive 1. And we keep going. How many times will x go into x? A positive 1 times. And you know what, ladies and gentlemen? We can stop right then and there because all we're looking for is the equation of a line. So the equation of this slant asymptote must be y equals x plus 1. So I'm going to show you exactly what this looks like in Desmos. Okay, here I have for you y equals x squared plus 1 over x minus 1. You'll notice it is the exact same rational function that we had over here in box number 2. I'm just giving you an actual picture of it. Okay, so looking at this graph, right, if I zoom out really, really far away, you can kind of see that there is an asymptote here, and it's on a slant. And we just figured out how to find it using long division. So if I turn this on, and I'll make this one dotted for you guys so you can kind of get a little, so you can get a better feel for it. So I'll make this dotted like that. Okay? So look, as you can see, right, for very, very large values of x, all of a sudden your function tends to behave like the line y equals x plus 1. I like this Desmos because it gives you a really good interpretation. Like way over here at 200, look, it's basically the same thing as y equals x plus 1. But if I zoom in really, 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 really close on this thing, it never actually touches the line. So asymptotes are a really cool thing to understand fully. So hopefully that makes sense to you guys. Okay, let's go ahead and find the slant asymptote, for example, number 2. I'll do this in green for you. The degree of p of x is 2. The degree of q of x is 1. They are separated by a value of 1. Therefore, I know a slant asymptote exists, and I can find it using long division. So I have x minus 3 divided into, I've got x squared minus 4x minus 5. Okay. X goes into x squared and x times x rather is x squared, excuse me. Negative 3 times x is negative 3x, and don't forget that we are subtracting all these things. You get 0 by design. Negative 4x minus a minus 3x is negative 4x plus 3x, which is just negative x. Bring down the negative 5. x goes into negative x negative 1 times. And you know what? We can stop because we have found the equation of a line. That would be y equals x minus 1. I'm going to graph this rational function for you in Desmos as well as the slant asymptote to get a better idea. Okay, here is the rational function, x squared minus 4x plus 5, which is, oh, I'm going to change that to minus 5, excuse me. Minus 5, my bad. Okay, divided by an x minus 3. So here, x squared minus 4x minus 5 divided by an x minus 3. And then we have the the slant asymptote at x minus 1. So I have plugged that in as y equals x minus 1. So taking a look at this rational function, if I zoom out a little bit more and move it around, you can kind of see that yes, there is a slant asymptote there. And if we turn this on, we can see that indeed, yep, that fits perfectly to that rational function. Okay, here you go. Box 3, you try. Find the slant asymptote. Okay, hopefully recognize that the degree of the top is 2, the degree of the bottom is 1, that's separated by a value of 1. We use long division and we come up with 2x minus 1 for the slant asymptote. And I check in Desmos where indeed, yes, the line 2x minus 1 is indeed acting like a asymptote for the rational function given to us of 2x squared minus 5x plus 7 over x minus 2.